Okay, so everyone is back after the coffee break. So just to explain to everybody something. So first things, if you see my virtual machine, okay, so you have seen that I have launched SAR Pro, and I have also opened two folders. So the share folder and the folder practical, Pulsar, and then you will have the PDF of the practical. And I have launched the first one, practical one. Okay, so I shall come back on that after. And in parallel, I have also launched the folder share dataset, Pulsar datasets, and San Francisco Hellos one. So this is the original, this is the raw data from Hellos we are going to process. Okay, first step. Now if I come back to the practical, okay, so this is the first slide. If I look to the second slide, okay, it's coming. So just to make the introduction that we shall process the San Francisco image, okay, and this is the flow chart we are going to follow, the processing shell. And you can see that we have different steps. The first step, configuration. The second step, data import. The third step, data geocoding. The fourth step, data process. And the last step about how to display some results. And here, concerning the two-step data import and data geocoding, it is written C, import polarimetric dataset. So this is another practical. This is another PDF file, which is not in your folder. Okay, it is not here in your folder. So we have to do this first. Means that we have to import the original raw data from Hellos 1 to convert the data to a compatible SAR Pro data format. So how we can do that? You are going to click on Education, on Practical. I'm going to close this. On Practical, do it yourself. And then you have the web page of the SAR Pro, which is open. Now, if you go down, let's reduce it a little bit. Up. If you go down, you will find the first part of the practical, in fact, here, which corresponds to the polarimetric dataset import. Okay? So this is what you have to do first. First, you have to do this one. So this is the PDF. If you click on the PDF, you can follow, and this is what you will have to do to import the dataset and then to geocode the dataset. And then after you can come back to the practical number one. Okay? It was the first point I wanted to mention. The second point I wanted to point out is if you click on lecture note here, you will open also. You have to close here. Oops. Okay. So if you click on lecture notes, you will open also the web page of SAR Pro, and here you have different notes, different lectures notes. We have written with Professor Bonner, or with Janssen Lee, with Laurent, and with Carlos Lopez. And we have also here the book I have presented to you this morning, which was recently published by HISA with Yves Desnos and Irena Hanchek about the polarimetric synthetic aperture radar principle and application. So if you click on it, you will have access to this book, which is open source, open free literature. Okay, so this can answer to a lot of questions you asked me this morning. So you can have access to this book online. Okay, and the first part I have written with Carlos Lopez concerns the basic principle of SAR Polarimetry, and so in fact it corresponds to what I have explained to you this morning. Can you put the link to that window in my Venn? I get okay. So the link is TTPS deux points tac faire. SAR Pro Bio. Education. And then oops. Okay. This is a page for the lecture notes. And the page for the practical. Oops. The page for the practical is the same, but instead of a lecture note, you have one page is for the notes and the other page is for the practical. Okay? So you have to start with the first one. You can download by yourself if you want. It's not a problem. Okay, so you can follow. It's not normally it's not difficult. Yeah, and if I remember, I think that in the middle, I have one or two questions. You will find the answer to the question. You can ping me and shall answer if it is the right answer. Yeah. Yeah, you see, you will get this kind of a question. Okay, when you will extract the data set, you will have this kind of question. Ouais, there is the input process for that and for you obtain the part of the image when performing geocoding and not sound image. Okay, so you apply the 7x1 multi-loop, but that. I'm going to do it with you. Okay, so it is here that you apply a 7x1 multi-look. Is it right? I think that if you apply a multi-look, snap, because it's not me it's not Polsapro who is going to apply the geocoding. Okay? I'm using snap, in fact. Behind. You don't see that, but I'm launching, I'm running snap in a batch mode. Okay, so maybe we need to have a full resolution as the input of the snap process. So this is why I have written not doing multi-looking. Okay? So this is why I prefer to do no multi-looking. I can create the T3. It's going to import and to extract and to convert in the T3 format, and then we shall apply the snap procedure to make the geocoding. So it's running. So in fact, what I have done, I have just import. I have tell Polsapro where is located the dataset, what kind of dataset it is. It is hellos one, etc., fully polarimetric format. And then I have imported and then extracted. So during the extraction, Polsapro is going to check all the pixels to see if there is a non-value or if there is an infinity value, and is going to create a mask, what I call a mask of valid pixel, which is represented here on the left part. So you can see that all pixels are red. In fact, it is a binary file. It's 0 and 1. And so here we can see that all the pixels are 1. So it means all the pixels are valid. There is no problem with the original raw data. Okay, and so this is what I get directly. So if I compare to the ground truth, we can see that the image is upside down. So it was one of my questions. Why the image is upside down compared to the ground truth? You can see if we compare to the ground truth, the north here is at the bottom of the image, and the south is at the top of the image. So the question is it a descending orbit or is it an ascending orbit? Depending to the orbit, yes, of course, it depends to the orbit, because it is in the geometry of the radar, yes, okay, perfect. So now the next question is it an ascending orbit or is it a descending orbit? Ascending, why? Because first, okay, yes, because the first row, here, the first row of the image at the top correspond to what the radar has seen during his first acquisition. And the last row of the image correspond to the radar has seen at the end of the acquisition. Okay, so he starts from the south and he stops from the north. So this is why the south is at the top of the image and the north is at the bottom of the image. So it means that the radar or the satellite is coming from the south to the north. So it is a ascending orbit. Okay. Because the top of the image is the south. Okay, perfect. Very good. Okay, so now what I proposed was to geocode the array. Before. If we look to the original folder, you can see that we have created a new folder which is named T3. This folder was not present at the beginning. So SAR Pro has created this folder during the data extraction. So what means T3? T3 means coherency matrix. T3, coherency matrix. And if you go inside this folder, you will see that you will find the binary file corresponding to each element of the coherency matrix. So I have the T11 binary file. I have the T22, the T33. The other parameters are complex parameters. So if they are complex parameters, it means that there is a real part and there is an imaginary part. So we create a binary file for the imaginary part of T12 element and a binary file for the real part of T12 element. Okay, so in fact, in conclusion, we have the nine binary file corresponding to all the elements of the 3x3 coherency matrix. And we've also associated HDR file, which is a text file, which is compatible with NV, and you have all the information. If I click on it, you have all the information concerning the corresponding binary file. You have the number of samples, number of lines, number of bounds. It is a complex value, and you have some information about the map info. So this is compatible with NV if you process data with NV. So you can read directly the binary file at the output of SAR Pro. Okay. So now we are going to geocode, and for this we are going to use utilities. We are going to use the functionality of a SNAP, Sentinel-1 toolbox, okay, and to geocode the T3. Okay. Not now. We are not going to apply a multi-loop before. I'm going to check by and I shall reply to it. Normally we can. So I'm going to see what is wrong, why it doesn't work. So now do it without multi-looking. Officially, I think we can, because if we enter the multi-look here, normally it must work. But anyway, I'm going to check. So you select LS, you select the volume file. Okay. So it means that the output is a square pixel. The pixel spacing will be 23 meters. So normally, now if you enter 7 by 1, if you apply first a multi-loop, normally if you change here, it must work. Normally it must work. I'm going to check why it doesn't work. Maybe Snap changed something, but normally it must work. I shall check. Well, anyway, so I have extracted without multi-looking. Okay, so I apply a bilinear method, SRTM, the bilinear DM resampling, etc., etc. So we can process. So I run the function, okay. And SAR Pro asks me if I want to create a new folder which corresponds to the geocoding dataset. So I say yes. And you will see that in the share folder, now we have created a new folder with the same name and with the suffix snap. So it means that this corresponds to the geocoding of the data. And if we go inside this folder, you will see that automatically we have created T3 because the input will be a T3 matrix and the output will be a T3 matrix. So once it will be finished, you will see appearing the mask, the new mask, and you will see appearing the new false color poly image. Okay, and so you can see here the evolution at the top, at the bottom of this widget. So now it's processing T13 as the imaginary part of the file, and etc., etc. Okay, now it's processing T22. It's geocoding T22. Then geocoding T23 and T33. No, I'm not going to remove. I'm just going to explain what we get here. Okay, so this is the result. This is the result. So you can see that now the image geocode, so I can overlay over Google. It's not a problem. So you can see that we get a good result. And now this is the starting point for the practical number one. Okay, so now you can come back to the PDF file corresponding to the practical number one, and then you can follow the different part of the exercise. Okay, so this will be the starting point. So if we check, is this a new folder? So the dataset folder with the snap. If we go inside, we have the T3, folder, and inside we have the different files. Now, what you are going to do, you are going to apply different polarimetric process on this image, and the result will be saved on the same directory. So everything is located on the same directory. Okay, so you have the T3 elements, and when you are going to process entropy binary file will be inside this folder, and the entropy, the combination, etc., etc. So everything is saved on the same folder, on the same dataset directory. Okay, so now you can come back to practical, pulsar, and practical number one. Okay, so we have just made the two first steps. We have import the data, and then we have geocode the data. So now you can apply a very, very simple data processing. It's just to have a look, to have a first qualitative analysis, something very, very simple. So I propose to you to display some elements of the T3 matrix, to apply the polarimetric entropy and entropy alpha decomposition, and to play with the entropy and the entropy, the combination, and try to recognize what I have explained to you during the presentation, and to conclude with segmentation using the very simple entropy and alpha plane. Okay, and to see if you recognize the different points I have presented to you. Okay, so this is the philosophy of the exercise. And now coming back to the question, does geocoding remove any of the polarimetric information in certain cases? No. It's not going to remove. It's not going to remove because this geocoding is applied, and the same geocoding procedure, the same parameters, is applied. It's like the speckle filter, is applied on individually on each element of the coherency matrix. Okay, so each element of the coherency matrix is geocoded with the same way, on the same way. So I'm not going to lose polarimetric information. However, remember what you have seen, I think, yesterday with the presentation of TUI, the 2N. The original SAR image is defined in the slant range domain. Okay? And in the geocoding process, we are going to project this image on the ground. Okay? So sometimes you can have some pixels in the slant range which are projected on the same pixel on the ground range. Okay? But all the elements are projected. So it means that the output, the result, will be a mix of the different scattering mechanisms which are projected in the same pixel. Okay, so when you have a flat terrain with no topography, when you project a slant to ground, there is not too much problems. The problem occurs when you have topography on your environment. In such a case, you know that you can have some artifact effects, like layover, like foreshortening. You can detect on the slant range image. During the geocoding, when you have topography, sometimes you can have some error during the projection. And here, you will have a lot of mixture of the scattering mechanism because you are going to lose the correlation of the phase during the projection. And this can lead to some misunderstanding. In our case, here it's not a problem because it's not a very, very strong topography, so the result will not be too much disturbed. Officially, what we have to do? Officially, we have to process polarimetric information, always in the slant range domain, always. Okay? We don't have to make any geocoding. We have always to process in the slant range because we keep the phase information. We don't change the phase information. And remember that polarimetry is the most important information is the phase, because the polarimetry means phase means polarimetry. So you have to take care with the phase. So you have to avoid to geocode. So you have to process the original data set in the slant range domain. Then the result of your data processing after can be projected. Okay? So this is why, if we come back to my virtual machine, in the utilities, we propose also the functionality geocode parameter. So what does it mean, geocode parameter? For example, I process entropy image directly on the original data. So directly on the slant range. And the result of the entropy is a parameter, a real parameter, not a complex one, a real parameter, no phase, okay, between 0 and 1. And this information I can project without any problem, So this is why we offer this possibility. So something, if you have time, not today, but when you will test again at home, something which can be very interesting to do. When you get original data, you stay in the radar configuration, in the radar domain, in the slant range, process. For example, you process the entropy, which is a parameter which is very sensitive. You process the entropy. And then you geocode the entropy. Okay. So I keep this information. Second step, I take the original data set, then I geocode the data set. Then I derive the entropy in the ground configuration. So I have a second entropy image. And then I compare my two entropy results. And here I can see if I am wrong or not. So sometimes like that, you can detect some pixels where you have a problem during the geocoding and where you have to take care when you want to process polarimetric information. Okay, so sometimes it's better to stay in the slant range to process than to geocode. So today it was just an example. It is just between us. It is just for you to train, to test this software, PolSAR Pro. So we are not going to take care of these errors. We consider in this exercise that everything is perfect in a ideal world. So I can geocode and then I can process. But keep in mind that you have to take care of the phase. And geocoding can affect the phase. So can affect the results of the polarimetric parameters. To the rope of a lot of things. I mean that modifying the snap geocoder to accept the material might involve some map for feeding parameters. Okay, but this is a problem of snap. Is it possible in PolSAR Pro to apply the same distinction to a series of acquisitions? I mean, if I have 5 acquisitions of the input at the same time. Okay, this is a very good question. So there is one of your colleagues. Yeah, she asked me the same question some months ago. So I derived something for her. So I derived a batch file. And I think that everything was working. So I'm trying to show you something. Oops, where is PolSAR Pro? Okay, so I'm going to launch another PolSAR Pro. Okay. So the answer of your question is in this bottom. You see in the bottom, PolSAR Pro batch mode. If you click on it, you will get this menu, but you can see that all steps are inactive because I have not finalized this routine, this procedure. And my objective is from this menu, you can enter all the LOS acquisition and you can run in a batch mode all the stack at the same time. And then to make a process on a series of acquisition. But today I have not finished. It takes some time to derive these functionalities, and it's on progress. Okay, on progress. But I know how to do because I did it already for Luciana, and maybe she can answer. And I think that everything was working quite well. So I have just to implement inside. So maybe in the next release or the next release, you will get it, but not today. Sorry. Now, another question. The place of decomposition, okay, and then I'm trying to perfectly provide the solution with the education as a direct download. Okay, so for Julia, concerning the strong topography, my advice is what I have explained. I should prefer to work on the slant range to keep the phase without any modification due to the geocoding, and then once I got all the results, then after I can geocode. Okay, so I would prefer to do this kind of approach. Pulsar Pro is scriptable. Yes, Pulsar Pro is scriptable. And to answer for Snap, this is what I'm doing with, you don't see, but when I launch Snap behind, in fact, I wrote a script, HTML script, which is read by Snap, and Snap runs the process. If you watch what's in the Trust window, it's easy to write a script in your language of choice. Yes, this is executable, so you can launch the executable file with a different argument you can find in the trace window. Yeah. The batch process saved my work. Okay, thank you, Luciana. Not related to the practical, I'm working with UFSR, circular position ratio data to create an unsupervised threshold map to determine if it's possible to create threshold map. Separate engine to separate using static. Yes, you can do it. Yes, you can do it. Okay, so if I understand, your input is a circular position ratio. Okay. To create threshold maps. Okay. So I can propose to you something. So you will have to play with in the utilities. Some years ago, I have created a calculator. Okay, so if I click on calculator, I get this. Oh. Okay. So it is a basic calculator. What does it mean? It means that I can apply a threshold on the parametric file parameter. I can apply different functionalities which are on the indicated on the right part. I can add a value. I can multiply by a value. I can take the cosine of the value, etc. So, for example, select operand 1. So I'm going to take a file. Okay, so you're going to ask me select the input binary file. Okay, so I'm going to take one file, for example, the T11 bin. Okay, so it detects it is a float type file. It detects the number of row, number of call. So I say okay. So now I can do different functionalities. So I have to select operator. It is the second step. Okay, so I can select. I put everything in the square, so I can select this square. So it means that the result will be T11 square, etc. Okay. So I can select also a threshold. If I select this functionality, it means I'm going to compare the value of the pixel to a threshold. Okay, so this is lower than this threshold or equal to this threshold. So here after that I can enter the value of the threshold, etc. Okay, so it is a basic calculator, and you can do this kind of thing if you want. In your case, compare or separate the pixel where the CPR is below 0.2, 0.3, and 0.3 and 0.4. Okay. Yes, this is something I could use. This is something which is very simple. Next question. Why? Good question. Bus calculator. Too much. Why the modulus are in grayscale and the phase are in color? Good question. Because I wanted to have something beautiful, so I put colors on the phase. I come back to the new question. I'm just going to answer to this. Okay. Okay, so the modulus, in fact, this corresponds to amplitude. So this corresponds to intensity. So from a visual point of view, usually it's more effective if I code the intensity in a gray scale. White for bright areas and black for, can we say, very, very low intensity areas. Okay, it is more, can we say, more easy to interpret the result. For example, here, if I look to T22, you can see that T22 is very white in the urban area. So it means that I have a lot of oops. So it means that I have a lot of intensity coming back from this area compared to the sea surface, where I have quite no intensity. So usually, we prefer to use grayscale, to code the intensity. And concerning the phase, we use color. Why? And we use a color map, which is a specific color map, which is a HSV color map. We know that the two most important color maps are the jet color map and the HSV color map. The jet color map vary from blue to red via green and yellow. Okay. The HSV color map starts from red and hand to red. So it's go from red to yellow to green to blue to magenta and then to red again. But you know that the phase starts from pi and hands to minus pi. But minus pi is equal to pi. So in fact, the starting point and the end point are the same. So the idea was to find a color map where the starting color is the same as the last color. Okay, so this is why we choose the HSV color map to display the phase information. Okay, so before extracting the threshold, would the 7x7 bin be efficient to smooth out the data and remove the speckled noise without? Yes. Yeah. 7x7 can be okay. The Shannon polarimetric is in Pulsar Pro. Yes, the channel. Yes. So I'm trying to up. So if you go to process, if you go to entropy, anisotropy, alpha decomposition, and if you select eigenvalue set parameter, the last one is Shannon entropy. Okay. So Shannon entropy is also proposed as a basic functionality. Okay, and it is constructed also from the eigenvalues. So this is why I have included the Shannon entropy functionality inside the menu of the entropy and anisotropy alpha decomposition. No. So if I come back, for example, to this, the window size row and the window size core, no, I have not applied a speckle filter. Okay, up to now I have just extracted the data, I have geocoded the data, and now I'm processing the data. I have not applied a speckle filter. you could ask to me why you have not applied a speckle filter. The reason is very simple, is that during the geocoding, as I explained, from the slant range to the ground range, some pixel will be projected on the same pixel on the ground range. So it means that somewhere a very small data averaging is applied. So it means that somewhere I have already applied a speckle filter. So it's not necessary to apply again a Lie filter, for example, okay, a speckle filter. So I have not applied a speckle filter. Here, what I propose is that when I derive any polarimetric parameter, we never know a priori what you have done before. So maybe you are going to process the entropy on a single look SAR image without any applying speckle filter. And so I can tell you that immediately what will be the result. So the result will be 0. Okay? Because if you do nothing, if you don't apply a speckle filter, by definition, the coherency matrix for each pixel will correspond to a pure target, so with a rank equal to 1. So by definition, the entropy will be equal to 0. Okay, so we need absolutely a rank 3. So we need absolutely to have a good estimation of the eigenvalues. We need absolutely to apply a very simple averaging. So this is why we propose to apply a boxcar, a very simple boxcar during the data processing. Okay, so this is why very often here I put 3 by 3. Okay, so 3 by 3. So like that, during the estimation of the eigenvalue, I shall apply a very small data averaging in order to get a rank 3 coherency matrix, in order to get non-zero eigenvalues. Okay, so it doesn't correspond to a refined Lie filter. It just corresponds to a sliding window. Okay, it is your last chance to make a special averaging before applying any data processing. The window size can be 1 if you want. Can be 1 because, as I said, during the geocoding, somewhere we have applied a very simple data averaging. So a very, very low multi-look. Okay, so you can make 1 by 1. So it was my question in my practical. So my question was, can you give to me a physical interpretation of this beautiful color image of the phase of the T12 element? Yes, so remember T12 is a correlation between HH plus VV and HH minus VV. So can you explain to me what does it mean? Yeah, it can be an answer. Phase doesn't change of the ocean because it's flat. Okay, so I shall come back to the Shannon bit. So the answer to this question is very simple. Concerning the physical interpretation of this image, my answer is I don't know. I don't know. I have not at all any idea about the physical interpretation of this image. I agree with you that it's strange. The phase seems to be the same in the ocean area. But what is the signification? What is the cause? I don't know. Remember that the T12 correspond to the correlation between HH plus VV and HV. Correspond to the correlation between single bonds and volume scattering. So my conclusion is this information means something. I don't know what, but it's very important. It means something. So the conclusion is that polarimetry is very important because you have a lot of information inside this image. Okay, so this is why if I isolate this phase, I cannot give a real interpretation of the meaning of this phase. But globally, if I use all the coherency matrix, it means that I have a lot of information, including this phase. So I have to process all the 3x3 coherency matrix to improve my understanding of the different physical scattering mechanisms. So while running the Shannon entropy, we had several outputs. So you have seen during my presentation before, but the difference between the classical entropy, so the entropy we introduced with the Shannon, the von Neumann entropy, and the Shannon entropy introduced by Refrégy and Maoyu. But the Shannon entropy is a function of two parameters, the intensity and the polarization. So remember, entropy provides to you the information of the randomness of the scattering mechanism inside the pixel. So the question is, if this randomness is due to a change of the intensity during the measurement, during the acquisition, or is this randomness is due to the change of polarization of the different scattering mechanism during the acquisition. So Shannon entropy is very powerful to answer to this question because it provides to you the information concerning the change due to the intensity during the acquisition or the change due to the polarization during the acquisition. So this is why we have different outputs. So you will have a Shannon entropy underscore I for intensity and Shannon entropy underscore P for polarization. Okay, so after I ask you to run the entropy and the entropy and to display the different combination and try to recognize what I have explained to you before about the physical interpretation of this combination. Okay. So this one is very important, the combination entropy multiplied by 1 minus anisotropy, as I explained before, because it is a very powerful detector of forest, non-forest. Forest and forest. It is something which is very interesting. Yes, you have 3 outputs. the total channel entropy, which is the sum of the polarimetric part and the intensity part, and you have each of them. Okay? The channel entropy corresponding to the polarization and the channel entropy corresponding to the intensity. And run this. Okay, so if we look to the free here. So on the right, you have the combination of the two. So on the right, it is the total channel entropy. And in the middle, you have the entropy due to the change of the intensity during the acquisition. And on the left, you have the entropy due to the change of the polarization during the acquisition. So what we can see here, we can see that on the surface, on the sea surface, during the acquisition, what the radar see, you see the sea surface. Okay. So the scattering will be quite the same. So the polarization coming back to the radar will be quite the same. So this is why the entropy is very low. It means that the polarization is consistent during the acquisition. But during the acquisition over mountains on the bottom or over park on the top here, for sure, by definition, due to the topography, due to the vegetation, due to the forest, the trees, etc., etc. So when I see the forest on the left side, it is not the same thing when I see the forest in front of me or when I see the forest on the right side. So for sure, the polarization is changing. Okay. So this is kind of information you can extract from this image. And in the middle, this is due to the intensity. So for sure, in the urban area, during the acquisition, sometimes you will be aligned with the street, sometimes you will be orthogonal to the street, sometimes you will see the buildings with a local incidence angle which is varied, changing. So for sure, by definition, you will have a flash. You will have a change, very strong changement of the intensity. So this is this information you can get here. But on the sea surface, well, you can see that sometimes it's changing a little bit because maybe the surface is more rough in certain area compared to other area. And then you can have a little change of the intensity, but the polarization is not changing. Something which is very nice is when you look to the airport here, the two blue lines here. This is our San Francisco airport. Yes, so the intensity is very low because it is like a mirror. You have nothing coming back to the radar. Okay, remember the radar is on the left of the image and is looking to the right. Okay, so the runway of the radar is like a mirror, so nothing is coming back. So everything is running quite well, I guess. It was. I have interesting question and I have not problems. So this is good. This is fine. It's good. Hopefully, you have no problems. Scattering predominance and diversity. Okay. And which model-based decomposition could perform better over an agriculture area that also include crops with medium height and DV? Oh, okay, scattering predominance and diversity. Okay, so we have two parameters. I don't know, diversity was defined by Thomas and Prof, I think. So it was a parametric parameter which provides the information of diversity of when you make the analysis of an extended target, open area. So which provide to you the information about, spatially speaking, the change of the polarization during the scattering interaction. Okay, so this is a diversity. Predominance, in fact, it is more or less the result of an equivalent of a model-based decomposition. If I take the model-based, the Freeman-Durden model-based decomposition I have proposed to you before, presented to you before, the output will be three parameters: Fs, Fd, Fv, single bonds, double bonds, volume. And these three parameters provide to you the information about what is the most important scattering mechanism which is present inside the pixel. So in fact, you apply this decomposition, you extract the three parameters, Fs, Fd, Fv. You apply a threshold, for example, or a superior operator. And like that, you can have the information about what is the predominant mechanism inside the pixel. Okay, so this is what I can say about scattering predominance. We use this kind of information some years ago to make some classification, to improve some classification. It was working. Which model-based decomposition could perform better? I have not the optimal answer. I have not the optimal answer. It depends on your application. Okay. For sure, the Freeman and Durden model-based decomposition, as I have explained to you, has some drawbacks because it can be applied only on extended area which present a reflection symmetry, which is not always the case. Okay. So I think that the thing, Yamaguchi and thing with the four components is quite okay. It's quite okay. When you want to do something about vegetation, I should select the Van Zyl and Arihi decomposition. I shall present this tomorrow. Only because the model of the vegetation they apply is a very improved model. It's difficult to implement, to run, sometimes it's difficult. But when it works, the decomposition provides very good results. So Van Zyl and Arihi. Arihi was his Japanese postdoc working in Mitsubishi in Tokyo. Okay, so concerning SAOCOM, what I have implemented a street map, and I have also implemented top SAR modes. Okay, so with Pulsar Pro, just to know it's not possible to do it because I have not SAOCOM dataset here on the virtual machine, just to simulate something. For example, import spaceborne SAOCOM. So quad pole. So you can see if I launch the SAOCOM toolbox, so I have to select the metadata file, and you can see here, which is not active, you can select the top SAR swatch. So from the metadata file, Pulsar Pro is able to check if it is a street map mode or if it is a top SAR mode. And in such a case, if it is in the top SAR mode, it asks you which swaps you want to process or you want to import. The metadata is, we are going to see the XML file. Okay, so I'm coming back. Why in the DB you can see the E3 DB? Which one? What do you mean? I3 DB? What is I3? Well, I shall come back to your question. Will the phase differ in ascending and descending paths for the summer? Yeah, for sure. Is there a way to combine both to extract information in terrain region? Yes, of course you can. You know, this is a problem of a radar. If the radar is looking from the left to the right, you will not see the same thing. It's looking from the right to the left. Okay. Because the configuration is a slant range. It's not the ground range. It is a slant range. So if you look in the ascending orbit or descending orbit, the slant range will be opposite. Okay, so the phase will not be the same by definition. Is there a way to use Pulsar Pro to show histogram for speckle distribution, gamma, and relay? Yes, yes, you can. Yes, you can. You can do a lot of things with Pulsar Pro. So I'm going to come back. Oops. If I remember, it is in process. Yeah, it is in a polarimetric data analysis. Okay, so you have some functionalities to derive some statistics, some histogram, some profile, some histogram-based statistics, some texture analysis. So we offer these functionalities. So the output will provide to you different data distribution, and you have also a confidence coefficient, which is going to compare your data distribution to a theoretical distribution like the gamma, the relay, the rise, the K distribution, if I remember. Okay, so metadata XAB or XML, so I have answered, is XML file. For the new RCM reader is an adapter for ScanSAR data include. ScanSAR, I don't remember if I have included ScanSAR. Because you know, when I implement a new sensor, in general, I interact with space agency, the corresponding space agency, and they provide to me some sample data sets. And we have an agreement, so I develop the toolbox, and then after I exchange, I interact with them to see if the result is okay or not. So it depends of the data set they provide to me. So I remember when I had some interaction with Konae, I receive a top SAR, I receive a street map in dual pole, in quad pole. For radar set 3, for RCM, we are going to simulate. Yes, donc import, spaceborne, radar RCM. Okay, so I have compact pole, I have dual pole, and I have quad pole. So I open the SAR product file, and I don't remember. No, I don't remember if I have processed a scan SAR. So a priori, I should say no. Okay, because I don't remember. Okay. Okay, so also one point you will see if you listen to the general presentation of the software. If you compare Pulsar Pro to the map platform that was presented yesterday, it's completely different. It's nothing to do. Pulsar Pro, when I started to develop Pulsar Pro, so it was in 2003, okay, the objective was to develop a toolbox, but with the right definition of what is a toolbox. A toolbox is a box of tools. Okay? So this is why we propose quite 2,000 or 2,500 different tools. That means different data processing functionalities. Okay? What you have seen with map, it is more close to like a QGIS. Okay, so you can do a lot of things, very beautiful things. And so the next step in the future, not in the long future, in the next months or the next years, is to import some functionalities of Pulsar Pro inside the map platform. So like that, you can have access to all the functionalities about which are offered by the map platform, and at the same time, you can process specific functionalities using the routine of Pulsar Pro. So you will not have this graphic user interface, which is imported inside the map platform. You will just have the functionalities, like for example, the Shannon entropy derivation or the Wishart classification, and these kind of things, which will be implemented inside the map platform. Okay, so remember, Pulsar Pro is a toolbox which has to be seen like a box of tools directly. Okay, so L3. Okay, good. Yes, I come back to L3. Yes, Pulsar Pro is what we have today. I will take it. I go there and I. Okay, so this is a general front page of the Pulsar Pro web server. So you can see that the new version is 6.0.3. I released 1st of May, okay, so some days ago. And you can download the Windows version or the Linux version, and it is the version you are using on the virtual machine. Okay, so it is exactly the same. So it is now public available on this web page. If we have a look to this web page, okay, so you can download the Windows version, you can download the Linux version. You cannot download today's plugin of Pulsar Pro with QGIS. I'm working on it. I have quite finished everything. I have just one missing functionality, just to display my results on the QGIS environment. And once it will be ready, I shall upload the plugin Pulsar Pro QGIS. So if you click on it, you will have under construction. Okay. On this, you can have access to the sample datasets. So sample dataset, this is what I explained to you. You can download the San Francisco Pulsar dataset. So you are using this image now, right now. Okay, so I provide before. On Thursday, you will use this polarimetric interferometric SAR dataset. So you have already put on the virtual machine. And on Friday, you will use this polarimetric tomography SAR dataset. And we have already put this dataset on the virtual machine. Okay. Tomorrow, during the lecture of Armando will explain the showcase dataset, so you can have access. Okay, you can have access to the different datasets you can use to illustrate the different showcases. Okay, about agriculture, cryosphere, forest, ocean, urban. So be careful. Sometimes it is very heavy dataset, like here, 3 gigabytes. Okay, for example. And if I come back to the page concerning the sample dataset, you have the GF3 dataset. So it was provided by the Chinese Space Agency. So I have the San Francisco, I have Paris in France, I have Rennes, my home city, I have a city in Morocco, and I have the South Pole if you want to do some cryosphere data analysis. So this is also a fully polarimetric dataset. And as I explained to you, we provide also different dataset on the same area, which is a test site, a super test site, which is the San Francisco area. So you have the dataset with SAR, LS1, LS2, GF3, RadarSat 2, RISAT, Sentinel-1, Sentinel-3, etc. And if I come back to the main page, you can have access also to the forum of Pulsar Pro, which is on the STEP forum. Okay, so you can have access also to Pulsar Pro, and you can ask a question, etc. And you have answer to your question. Okay, so you have the dedicated page to Pulsar Pro. Okay, so you can download. So after the course this evening, you can download and you can install on your own machine the Windows version or the Linux version, and everything is explained in the installation procedure, what you have to do for the first time. So you have to first of all install the TCL/TK kernel. You have to install GIMP. You have to install ImageMagick. You have to install Snap. You have to install Google Earth, and then after you have to install Pulsar Pro, and you will have also the configuration. So once you will launch for the first time Pulsar Pro asks you different questions, asks you to enter the link between Pulsar Pro and PDF reader, the link between Pulsar Pro and Snap, between Pulsar Pro and GIMP, etc., etc. And after that, everything will be configured, and then you can run the software as like today. Okay, so this version is we use in the course. I had also a question from Luciana. L3. Okay, so L3 correspond to the third eigenvalues. Okay, so it corresponds to the lower eigenvalues. So it is really very sensitive to a very, very small scattering mechanism which occur inside the pixel. So this is why you can see the wave, which are very, very specific scattering mechanism. Okay, so L1, lambda 1, in fact, L for lambda 1, correspond to the dominant scattering mechanism. L2 to the medium scattering mechanism, and L3 to the lowest scattering mechanism. No more questions? So everyone succeed to do the practical, to do everything? To play a little bit with the software. So we shall use this Pulsar Pro software on Thursday to illustrate the practical on Polarimetry, and we shall use also this software on Friday to illustrate the Paul SAR. Okay? And in fact, everything, you switch from one mode to another mode when you select the environment. Today we select single dataset because we are going to process, or we have processed, only one SAR image. So we are in the case of a Paul SAR. On Thursday, you will select a dual dataset because we shall process polarimetric interferometric. So you will see that on Thursday you will have to enter the master folder and the slave folder, okay, for the interferometry. And on Friday, you will select a multi-dataset, so which correspond to time series or polarimetric tomographic SAR. Okay, so you will have, we shall explain to you how to use this widget. So you can enter different folders. So each time you enter one folder, you increase the number of folders. So 1, 2, 3, 4, 5, 6. So we shall play with the 6 different folders, which correspond to 6 different tracks. So which correspond to 6 different acquisitions. And so like that, you can have access to the tomography functionalities, dedicated functionalities. Okay. But don't worry, I shall be online on Thursday afternoon and on Friday afternoon to help in Rennes for the Polarimetry practical, and to help also Laurent for the SAR practical.